Guitar solos have been around since the late 1700s, with music specifically written for classical guitars. But when you hear the words guitar solo, you probably aren't thinking of something like this, but something more like this. The electric guitar was created in the 1930s as a way for guitars to be heard above the growing orchestras of big band music. Since then, they've become a staple in many different genres. After decades of various musicians experimenting with the instrument, no matter the song, there's always more to an electric guitar solo than just fretting and plucking. Take Jeff Beck's version of Goodbye Pork Pie Hat, for example. With no vocals, the main melody and expression are left to the guitar. The various playing techniques can make the guitar sound like it's singing, but what's the physics behind all those different sounds? A quick review of everyone's favorite course might help. When you pluck a guitar string, you're creating a standing wave that oscillates and produces a sound wave. We can calculate the frequency of the standing wave if we know the wave's speed and string length, and the fundamental frequency corresponds to the musical note that we hear. A higher frequency giving us a higher note. When we fret a note, we change the length of the string, so the frequency changes. But the frets on a guitar make it so you can only fret a distinct series of frequencies. How do guitarists manage to bend notes? They bend the strings. When a player bends a string, they're changing both the length of the string and its tension. By using cosine to reflect the changing string length and adding a variable for extension force to the tension, we can find the new frequency. Summarizing the work of David Grimes, if we use Hooke's law to express the extension force in terms of the string's cross-sectional area, its stiffness, and the bend angle, we end with this equation to determine frequency. Since, during playing, the material and initial length of the string stays the same, the only independent variable in the equation is the bend angle. Modeling this equation, we see that increasing bend angle increases frequency in a nonlinear relationship. So when a string is bent, the pitch goes up. This can be used for vibrato, fluctuating the pitch and making the guitar more expressive. Another technique to change the pitch beyond simply fretting is to use harmonics. There are many different ways to use harmonics. Pinch harmonics use the thumb of the picking hand, while natural harmonics use the fretting hand. No matter the method, the theory is the same. The main note that we hear when a string is plucked is the fundamental harmonic, with only nodes at the boundaries, but there are simultaneously many other harmonics with more than just two notes. When a guitar player lightly puts their finger on a node of one of the harmonic waves, they deaden the fundamental frequency of the other harmonies, and the undamped harmonic can clearly be heard. Essentially, their finger works as a node without becoming a boundary. This is why playing a harmonic and fretting in the same place usually produce two different notes. Other fun sounds can come out of experimentation with audio processing, like distortion. Compare the guitar at the beginning of Goodbye Pork Pie Hat to that in the middle. It goes from clean to fuzzy because of distortion. An important step in the journey of a signal from the electric guitar to a speaker is the preamp. The preamp is what changes the timbre of the incoming signal, altering the loudness of the overtones. When a preamp is overdriven, that is, it's pushed to its limit with a very loud signal, specific overtones become more prominent. Interestingly, the specific overtones produced depends on the type of amp and whether it produces mainly even or odd harmonics. To understand why even harmonics are usually preferred, we need to use some music theory. Say we play an A, which means our fundamental frequency is 440 Hz. The second harmonic, then, is 2 times 440, and the fourth harmonic is 4 times 440. Both of these are also A's, just at higher octaves. On the other side, the third harmonic of A is 3 times 440, or 1320. This is an E, which is a fifth from A. And the fifth harmonic is 2200 Hz, a C sharp, or a major third from A. Fifths and major thirds are pleasant intervals to listen to, but if you're playing an A major chord, suddenly you have A, C sharp, and E all as fundamental frequencies. While the added octaves maintain the same chord, the odd harmonics add notes like F natural, the major third of C sharp but minor second of E, which sounds dissonant. Even or odd harmonics come from the shape of the sound wave. A preamp has 2 voltage limits, and an overdriven amp reaches the high limit first, clipping the top of an incoming sound wave. This causes an asymmetrical wave, which can produce even harmonics. When the lower voltage limit is also reached, the wave becomes symmetric. Symmetric waves produce only odd harmonies. And so we've got bending, harmonics, and distortion all playing on different equations and physics principles to produce some pretty awesome music. Thank you so much for listening, and goodbye, Pork Pie Hat.